Good morning. Welcome to the WEF Membrane 101 webcast. I'm Paul Schuler with GE Water, and I'll be your host today. This webcast is co-sponsored by the Municipal Wastewater Treatment Plant Design Committee and the Students and Young Professionals Committee. This webcast is part of the Fundamentals of Wastewater series being developed by the Municipal Wastewater Treatment Plant Design Committee. I want to give special thanks to Hannah Wilner of CH2M Hill, who organized this webcast. We have three great young professionals with talks today. I hope you enjoy the webcast and learn something too. Some quick housekeeping. Send questions to the speakers at any time using the pop-up tabs on the screen. We'll answer a few questions after each talk, and we'll do a Q&A period for all speakers at the end. You can get a copy of the slides using an instruction sent to your organizer. There's an FTP site for download. So let's get started. Our first speaker is Adrienne Minetti, a process engineer with CH2M Hill in Portland, Oregon, and she'll discuss membrane fundamentals. Adrienne?
Thanks, Paul. Good morning. Give me just 1 second while I get my slides working here. There we go. So before I jump into the presentation, I'd just like to give you an idea of the objectives for this first half-hour presentation. The first one really is to introduce membrane terminology and basic operating principles so that in the next two presentations you have some background on the vocabulary words that will be thrown around. And then to compare the infrastructure and decision drivers of membrane bioreactors and tertiary membrane filtration. And finally, just to provide a general membrane project overview. So why is it that membranes have garnered so much interest recently? And I really like this slide as an illustration of why it is that membranes, the applications are rising so significantly. If we think about the life cycle of water, starts out as groundwater or surface water, and we treat it to a pretty high level, generating drinking water, where of course it gets dirty. Turns into wastewater, and then we treat it again. When we start to want to reuse that wastewater, we have a need to generate a much higher quality effluent than conventional wastewater treatment provides. And here really is where membranes are a key application because they provide a really high level of treatment for reclaimed water. So what are the uses of reclaimed water? I think it's no surprise to anyone that there are a variety of uses for reclaimed water. And a lot of what this water will be used for is driven by what's close to the treatment facility and really what the objectives are for going towards water reuse. Okay, so we've established membranes are great, but what is a membrane really? A membrane is a thin, semi-permeable polymeric film adhered to a support surface that retains some substances but not others. What does that really mean? So here's a very close-up view of a membrane. This would be a hollow fiber, and on the surface of this membrane we see that we have some pores here. And again, the treatment of this membrane is driven by the pore size, which is shown in this picture here. So in fact, there are a variety of different types of membranes in filtration, starting with media filtration and getting to a higher quality as we go down the line. So membrane bioreactors and tertiary membrane filters are in the microfiltration and ultrafiltration size range. And really what that means is that the pore size of the membrane is in the 0.1 to 0.5 micron range for microfiltration or around 0.01 micron for ultrafiltration. So tertiary membrane filtration and MBRs are both membrane processes, and so this is just an illustration of how they differ. A tertiary membrane filter is placed at the end of a conventional activated sludge system and treats the water that comes after the clarifier, whereas an MBR, the membrane essentially replaces the clarifier. So once we start to go to membranes, we need a driving force. So we have a membrane, and the membrane cleans the water, and there needs to be some sort of driving force to get the water to pass through the pores of the membrane, and that driving force is pressure. So there are two ways that we can configure membrane systems, and the first way is called a pressurized system. And what this means is essentially we pressurize the feed water to the membrane and force the water through the membrane in that direction, as opposed to submerged, where we actually draw a vacuum on the effluent. And so the driving force comes from having atmospheric on the feed water side and a vacuum on the clean water side. So when we look at different types of filters, very often, and these are general types of filters, what you'll see with tertiary membrane systems is hollow fiber, either pressurized or submerged. Whereas in MBRs, though you do see some pressurized systems, by and large they're submerged systems, and you'll see both submerged hollow fibers and submerged flat sheets. So more membrane terminology. A membrane system starts with an individual membrane, and those individual membranes are grouped together in modules. From the module, when the groups of modules are then collected into trains, and then these trains add up to equal the whole system. All right, more key membrane vocabulary. So this box here represents an idealized membrane, and the feed water comes in with dirty water. This is essentially the dirty water, and it goes to the membrane, which would be sort of represented as that active layer here, and the constituents are concentrated and removed, and the clean water passes through. Clean water in membrane systems is referred to as permeate or filtrate, whereas that concentrated solution of contaminants in tertiary membrane filtration would be called retentate or concentrate. In MBRs, if we recall, we've replaced the membrane or the clarifier with the membrane. So this concentrated stream is in fact the biomass that's doing the treatment of the wastewater constituents. And so in an MBR, this is return activated sludge or mixed liquor. So second key vocabulary term, flux. Flux is essentially a loading rate on the filter. And so it's the flow rate per unit membrane area. And in American units, it would be gallons per square foot of membrane area per day. If we were in metric units, it's often liters per square meter per hour, or LMH. So we talk a little bit about the driving force of membranes, and that really is a difference in pressure. And maybe it's not such a surprise that that difference in pressure is in fact the transmembrane pressure. And what you'll see often is in fact that the flux and transmembrane pressure, well, in fact it happens to be that the flux and transmembrane pressure are related. And so it's sometimes nice to refer to them in one single unit, which is called permeability or specific flux. And this is just the flux of the membrane divided by the transmembrane pressure. So as I mentioned, the flux and the transmembrane pressure are directly related. And so what that means is if you want to increase the flux, then you're also going to increase the driving force required to generate that flux. And they're pretty linearly related if we have clean water. However, if there's contaminants in the water that we're trying to remove, we find that we lose the linearity of the relationship. So essentially what that means is that it's harder, as the membrane fouls, to generate the same flux that we want. So, for instance, in membranes, we could fix the flux, and then as the membrane fouls, the transmembrane pressure will change. Alternately, we could fix the transmembrane pressure, and as the membrane fouls, the flux changes. So membrane fouling, by definition, is essentially the accumulation of these contaminants on the membrane surface or inside the pores that reduces the production of the membrane. So as I mentioned, membrane fouling reduces the production of product water through the membrane. So as the membrane fouls, it's harder and harder to pull the same flow rate through the membrane. By and large, membranes and water and wastewater applications are operated to achieve constant flux. So essentially what that means is we fix the flux, and we watch the transmembrane pressure change as fouling occurs. And maybe just to restate this once more, when we fix the flux, as the membrane fouls, it becomes harder and harder to generate that same flux. And so we need a higher driving force to get the water through the membrane. This is an indication of membrane fouling. Membrane fouling. This is kind of the bane of a membrane system, and we spend a lot of time and energy controlling this fouling that occurs. So what are the things in the dirty water, which would be, for instance, the mixed liquor in an MBR or the clarifier effluent and a tertiary membrane filtration that cause membrane fouling? So we have colloids, which are just small particles, and macromolecules, which are large individual molecules, things like proteins and carbohydrates. We have suspended solids. The degree to which we have suspended solids, of course, is going to be pretty different between an MBR or a tertiary membrane filter. And for instance, in an MBR, those suspended solids are activated sludge flocks, or the bacteria embedded together as a group. We'll get some inorganic precipitation, and we'll have some biofilm growth. So as we operate the membrane, what we're doing is convecting water and all these constituents or membrane foulants right to the membrane surface. We generate treated water, and we get a concentrated mass of those things on the membrane surface that cause fouling. So this fouling, these are sort of general terms that characterize the different types of fouling that happen. Absorption is, for instance, the chemical interaction between things like macromolecules and the membrane surface. Pore blocking would happen when these colloidal particles, which happen to be pretty close to the pore size of the membrane, block the pores or accumulate inside. Precipitation can happen. Biofilm growth, again, we've concentrated all of these things on the membrane surface, so we can imagine this presents a very nice concentrated food source for organisms that might like to grow right on the membrane surface. And then we get the accumulation of these suspended solids that create a cake layer, which is, in essence, filter blinding. So as I mentioned, there are a variety of things that we do to control membrane fouling. And they're sort of classified into two different, so we classify them as either physical fouling control or chemical fouling control. And the way these things are applied will differ if you're looking at a different membrane vendor or a different membrane application. So the first thing that we can do is to keep the flux low. The flux essentially is, as we're drawing water through the membrane, we're pulling all those contaminants right to the membrane surface. So if we limit the flux, we limit deposition. It helps us to limit fouling. The second thing we can do is generate cross flow with air or water. And in fact, in membrane bioreactors, air scour is a really key way that fouling is controlled. And the idea here is just to generate shear along the membrane surface, and that creates sort of a backflow of contaminants to remove them away from the membrane surface. Relaxation is used in MBRs, where essentially we turn the flux off and only air scour. And again, this eliminates the forward flow of membrane foulants and maximizes the reverse flow. And then we see this back pulse, backwash more in tertiary membrane filtration. And the idea is to take treated water and reverse the flow through the pore, sort of blowing these contaminants or foulants off the membrane surface. The second class of fouling control is chemical fouling control, and this is just generally called chemical cleaning, which means that we clean the membranes with bases or oxidants, very often chlorine, to remove those macromolecules, the biofilms that accumulate, and acids to dissolve inorganic precipitates. So there are two scales of chemical cleaning that we see with membrane applications. And the first one is called a chemically enhanced backwash or a maintenance clean. And the idea here is that it's short duration. It happens most often when the tanks are still full with the feed water. It happens over 1 to 2 hours, daily or weekly, and chemicals like chlorine may be injected with that backwash water to sort of maintain the flux through the membrane. So the idea here with this chemically enhanced backwash is that we want to extend the interval between the more intense clean in place or recovery cleans. So these are longer duration cleans. They last 4 to 8 hours. And these things require the membrane tanks to be taken offline. So the membrane tanks are taken offline, and the tank is filled with a series of chemicals, again, bases, acids, oxidants, and the membrane is really thoroughly cleaned. So because we use so much of our energy, I guess, or we're spending a lot of time dealing with fouling, this creates the need for all these ancillary systems to let us do chemical cleaning and physical cleaning. And so for MBRs and for tertiary membranes, you'll find that you'll need also chemical cleaning systems, and I think you'll see a very nice illustration of this in the case studies of what all kind of goes into these extra cleaning systems. So you'll need chemical cleaning systems and then also physical cleaning systems like blowers for air scour or pumps for backwash. All right, there are one or two pieces of vocabulary that relate just directly to tertiary membrane filtration. And so in tertiary membrane filtration, we have the feed water. We produce permeate with a certain instantaneous flux. So this is what the flow rate that comes right through the membrane. However, some of that water is used for chemical cleaning. We actually use treated water to make the solutions for chemical cleaning, and some of it may be used for backwash. And so we lose some of that product water that we generate so that we get, in the end, a net production which is not necessarily the same as this instantaneous flux. So then here comes the idea of recovery, which is the efficiency with which this feed water is converted into product water. So the more we have to clean, the lower the recovery. All right, so I've gone through and covered a lot of the basic membrane terminology. And in fact, the membranes in both tertiary membrane filtration and MBR fundamentally work on the same principles. They use, by and large, the same vocabulary. They're just a different application condition. So the next part of this little introductory presentation will look at a comparison between two systems treating, for instance, the same volume of wastewater, either using tertiary membrane filtration or MBR. So one piece that I'd just like to remind you of is that with an MBR, with the air scour, it generates an oxygenated return flow. All right, relative comparison between the two. I think some of this won't be a surprise, and some of it actually, as I learned about membranes, was kind of a surprise to me. So the first one is land use required. You know, you still have a clarifier with tertiary membrane filtration, so you can imagine that that means that you need more land area. For similar reasons, there's two processes to operate with a tertiary membrane filter, an activated sludge system, and the filter. Both are membrane processes. Both produce great quality effluent. But if you want to start to do things like decentralized treatment, tertiary membrane filtration really is not an option because you have the clarifier to operate. With an MBR, you have an absolute barrier. It doesn't matter what the biomass is doing. It'll be retained by the membrane. Can be very highly automated. So MBRs are good for decentralized or unstaffed operation potential. The capital cost, for instance, for a greenfield project may be higher with a tertiary membrane system just because you have more tanks and more processes. However, the operating cost for an MBR, by and large, because of that air scour, will be higher. So if we look at the biological process solids concentration, much higher with an MBR. However, if we look at the solids concentration at the membrane, and this is really a key difference, I mean, you're seeing the effluent of a clarifier with a tertiary membrane filter, whereas the MBR is seeing the mixed liquor concentration. So maybe the best way to think about this is, this would be the kind of the concentration of foulants at the membrane. You can imagine with a low concentration of foulants, much less membrane fouling compared to this very high 8 to 12 gram per liter solids that the membrane is seeing. That is a really major difference between the two. And lastly, I mentioned this highly aerated return stream that we get for an MBR, and when we start to want to do biological nutrient removal, we have to stop and think about how to accomplish that. So it's just a little bit more challenging with an MBR than with a tertiary filter. So if you, or if me as an engineer or as an operator are looking at water reuse and wondering which application makes the most sense for me, there are a couple of different questions that you can start to ask that will separate out the decision drivers. So one key one is, are your reuse water users seasonal? If you have 10 mgd of wastewater that you're treating, but you only have 1 mgd of reuse water users lined up, a tertiary membrane filter may be a better application there because you can turn the system off in the winter. If you have significant seasonal wet weather flows, again, we talked about how we can decrease the flux to minimize membrane fouling, but similarly, if we increase the flux, you have a high concentration of membrane foulants in an MBR. You are pulling more of those foulants right to the membrane surface, and so it makes it very difficult to control the membrane fouling when you need to crank the flow up in an MBR. If you have significant seasonal wet weather flows, a tertiary membrane filter is much more forgiving and may be a better option, though I have seen in some very creative ways that MBRs have been applied and then kind of worked around with the seasonal wet weather flow issue. If your plant relies on BioP but has a very low phosphorus limit, a tertiary membrane filter is, it may be easier for you because you can do a chemical polishing step after the clarifier and then remove the metal salts with the filter. And this is important because adding metal salts to a biological BioP system can really hinder the recovery if you have an upset. So it may be that this tertiary filter makes your life easier with BioP removal and a low phosphorus limit where you would need chemical polishing at times. And sometimes it's just not possible to retrofit to an MBR. Now, things that might drive you towards an MBR, the land use requirements can drive that, and we've mentioned this decentralized treatment. Again, MBRs, because of that absolute barrier, retains biomass. It's pretty simple to operate. There's no washout problems like you have in a clarifier. All right, so now you've decided that you want to do membrane system, and the question kind of is, well, how does that happen? What's the best way to approach the design of these things? And in essence, you really can't start to procure a membrane before 15% design because the vendors really need to have an idea of what you're asking out of the membrane system. So you need to really define those site-specific parameters, the operating characteristics, the redundancy requirements. However, you really, if possible, would prefer to procure before 30% because all the systems are different. And so if you can do your more detailed design around a specific vendor, that's really the preferred approach. So what about piloting? In an MBR, it turns out we can pretty reliably predict how the membrane will perform, what their cleaning requirements are, and so really in terms of membrane performance, piloting generally isn't required. However, we've talked about this aerated stream and nutrient removal with MBR, so it may be a more complex applications or more challenging applications. We may want to pilot the biological process to figure out recycle rates and configuration. Often with tertiary membrane filters, piloting is preferred, and it's important to note that piloting, especially with multiple vendors and big systems, can be expensive. So you know, it would be nice to pilot before the project. On a large project, though, on smaller ones, what you may do is to procure a membrane and pilot afterwards, or have a demonstration period afterwards to really show that the system will perform based on what is expected. And then lastly, you know, moving on to detailed design. The equipment is unique to each vendor, and it's really beneficial to know what that equipment will be, what the flow rates are before completing the detailed design of the plant. So with that, we've talked a lot about membrane vocabulary, flux, permeability, transmembrane pressure. We've talked about membrane fouling and cleaning, and general membrane process overview. From here, this will carry on to the case studies, and I'd be happy to answer any questions you have.
Okay, thanks, Adrian. That was a great presentation, talking about all the fundamentals. There's a question regarding external membranes specific to membrane bioreactors. Is it right that an external membrane unit non-submerged membrane can you use in both an MBR or a tertiary membrane filter?
In principle, yes. So you often don't see an external pressurized system with MBRs. But, I mean, they do exist. And in industrial applications, sometimes you do see those external membranes.
Okay, thanks. Next question is specific to MBR. You said something that I think might be, I don't want to say controversial, but interesting to the industry, specific to BNR. Why is BNR more easy to achieve in tertiary membrane than an MBR?
Yeah,
Multiple processes. My intention is not to start controversy. It's just really to point out that the way that we do BNR conventionally is to have recycle streams to anoxic and anaerobic zones, and so you really need to think about the fact that you have a highly aerated stream coming back, and you really can't put that into an anoxic or anaerobic zone. It could really mess with the process. So I think it's certainly achievable, and it's happening all over that it is achievable. It's just something to think about starting off, and it's something that I think, for me at least, when I was learning membranes, someone kind of needed to point that out to me. It was something that is just, a piece of information to keep in your pocket as you move forward. Okay, thank you very much. Okay, that's it for questions. We'll have more. Keep sending them because we'll have more question and answer period afterwards, after the third speaker. Our second speaker today is Benita Saberwal. Benita is a process engineer with Black & Veatch in Atlanta, Georgia. She's going to talk about a case study for a large MBR in Arizona. Benita?
Thanks, Paul. Hello, everybody. I will be talking about MBR case study. I'll be talking about Butler Drive Water Reclamation Facility, which is currently designed for 10 MGD annual average flow with a future ultimate build-out of 13 MGD. Just to give you an outline, we'll give you a project overview and then go into design criteria. Then I'll talk about why MBRs were selected for this facility. Then I'll talk about the key design features and then discuss startup and operations at the facility. Here's the location for Butler Drive Water Reclamation Facility. It is in Peoria in Arizona. Peoria is a suburb of Phoenix and one of the fastest growing cities in the United States. Butler Water Reclamation Facility is a greenfield plant. This slide shows the site map. You can see the Butler IPS, which is the influent pump station, which is off-site, and here's the main plant. There's the effluent line which goes to aquifer recharge. The city earns water storage credits by returning reclaimed water to the groundwater system through percolation, which will allow the city to extract equal amount of water from the aquifer to meet future potable water needs. This site is bordered by agricultural and commercial properties with residences less than half mile away. Here are the design flows. The plant, for the initial phase, the plant is designed for 10 MGD annual average flow, and the future ultimate build-out would be 13 MGD. The point to note on the slide is the peak instantaneous flow through the headworks is 2.5 times the annual average flows, whereas the peak instantaneous through the membranes is only twice the annual average flows, and I'll talk a little bit more about this in my few slides down. Here are the design wastewater characteristics. As you can see, for the initial and future conditions, the BOD, TSS, and TKN are really different. This is because in the initial phase, the plant treats solids from another facility. When the Butler Drive is expanded to 13 MGD, solids at the other facility will be treated on site, and will no longer discharge to Butler Drive collection system. The initial aeration basins will have sufficient volume to treat 13 MGD without additional solids load from other facilities. With this design approach, city was able to delay solids processing facilities at their treatment plant. The plant has to meet effluent quality standards. It has to meet Class A+ reclaimed water set by Arizona Department of Environmental Quality and Aquifer Protection Permit. It has to meet turbidity less than 2 NTU on a 24-hour average with maximum not to exceed 5 NTU. Total nitrogen less than 10 milligrams per liter with an alert at 8 milligrams per liter. So really the plant was designed around the 8 milligram per liter goal. Fecal coliform no detect in 4 out of 7 samples with a single sample maximum of 23 CFU per 100 ml. Process selection. A key consideration for process selection was compatibility of the new treatment facility with its surroundings, population growth, and community acceptance. 3 technologies were chosen: conventional activated sludge, membrane bioreactors, and sequencing batch reactors. Out of these 3, 2 were shortlisted and further evaluated, which were conventional activated sludge and membrane bioreactors, and they were evaluated based on various factors which are listed on the slide, which I'll go over one by one. Cost, I will talk about cost on my next slide. Proven technology, conventional is well known. Membrane technology itself is proven, but wastewater application is emerging status. Odor control, both technologies were equal. On mechanical simplicity, both use conventional equipment, but MBRs use more of it. Process stability, conventional is subject to biological process upsets. MBRs are unaffected by biological process upsets, and bulking issues are eliminated in MBRs. Staffing requirement, MBRs require fewer operators to maintain biological process and handle solids. Effluent quality, conventional can easily achieve a turbidity of less than 2 NTUs, and MBRs can achieve less than 0.1 NTU. Expandability, both are equal. Footprint, of course, MBRs are smaller. Noise containment, both are equal. Visual aesthetics, MBRs are more compact with fewer structures. Solids processing, MBRs eliminate need for sludge holding basins and provide greater degree of solid stabilization. This slide shows the cost comparison between the conventional and MBRs, and as you can see, the construction cost came out to be 8% less, whereas the operating cost came out to be 20% more versus conventional. The 20-year present worth were very similar between the two. So MBR technology was selected because it was similar in cost to conventional treatment while offering benefits in terms of reduced footprint, process stability, exceptional effluent quality, and ease of operations. Membrane procurement. The project team used a qualifications-based process to pre-select the membrane supplier. The team presented a request for qualifications to 3 potential membrane suppliers, and it was based on a 100-point system, and each of the supplier was rated on that scale. The 4 main categories were corporate stability and financial capabilities. Under this, the membrane suppliers were required to submit detailed descriptions on ownership structure, financial statements, and bonding capabilities. They were also required to disclose any lawsuits or bankruptcies. The next category was experience, qualifications, and manufacturing capabilities, which included information on comparable sized facilities operating inside and outside of the United States. Next was demonstration of successfully operating facilities. This included detailed questionnaires on design and operation of at least 3 North American installations that were in service for at least 2 years. Equipment service, support, and maintenance capabilities. This included details on the locations of service staff and spare parts, startup and training capabilities. Here is a process schematic for the Butler Drive water reclamation facility. The facility consists of an off-site and flint pump station with mechanical clean bar racks. On-site, it has the on-site headworks has vortex grid units and fine screens. The raw wastewater flows to the headworks into the BNR trains, which has anoxic cells and oxic cells. The mixed liquor is transferred. Actually, it's pumped from the oxic zone to the membrane tanks, and the permeate from the membrane goes to the UV reactors for disinfection and out to the aquifer recharge. The return activated sludge flows by gravity back to the head of the oxic zone, and there is a separate independent nitrate recycle from the end of the oxic zone to upstream of the first anoxic cell. Solids handling facilities are limited to centrifuges for dewatering. Dewatered cake is disposed of to a landfill. This slide shows a cutaway view of Butler Water Reclamation Facility model. Here's a location of various processes. You can see the headworks located here, the 4 biological treatment basins followed by membranes, UV disinfection, is the blower building, chemical storage and feed, dewatering centrifuges, and the operations building. The facility has infrastructure in place for its build-out capacity of 13 MGD. The membrane quantity initially installed gives facility 10 MGD of capacity. As population and wastewater flow increase, additional membranes will be installed to increase the plant capacity to 13 MGD.
Benita, could you speak up a little bit?
Yes, sure.
Thank you.
Is it any better?
I think that is. Thank you.
Okay. Process design. The plant was designed for a total SRT of 12 days at maximum and 15 days at annual average. The target mixed liquor suspended solids in the aeration basin was 10,000 milligrams per liter. The design membrane flux is in the table on the slide for the initial as well as future 13 MGD condition. These flux, the membrane flux are calculated based on all trains and cassettes in service. So with one train out of service, it will be slightly lower than these values. Preliminary treatment and equalization. The plant was designed with 2 sets of screens to protect membranes. There were half-inch bar racks at the off-site pump station and 2 mm fine screens on site. For large plants, it is very beneficial since this reduces the amount of fine screening production and also reduces load on the fine screens. Flow equalization is very important for MBRs. Membrane sizing is hydraulically driven, so alternatives to increasing the number of membranes should be considered if the peak flow is more than twice the average flow. Designing membranes to accommodate higher peak flows typically results in flux rates at average flow which are below the optimized point and significantly increase equipment cost. As I showed you earlier in the slide, the design peak flow rate for the membranes is less through the headworks and into the MBR process. 2.5 Q coming in, and out of the membrane, that's 2 Q going out. The flow dampening is achieved by variable water level in the biological treatment drains. The normal water depth is 18 feet. During a peak event, the water depth can increase to 2 feet. So this plant has internal equalization. Here's a picture of fine screens. The plant has 3 screens on site with 2 mm openings. This slide shows the detail of the process through the MBR process. The degraded and screened effluent comes into the anoxic basins. There are 4 aeration basins, and each on the upstream of each aeration basins there are 3 anoxic cells. So the influent comes into the first anoxic cells, goes through the 3 cells in series, and then flows into the aeration basin and out into the mixed liquor channel, where it combines with the mixed liquor from all the 4 tanks and flows to the recirculation pump station. The mixed liquor is transferred from the recirculation pump station to upstream of upstream of membrane tanks, where this is the upstream distribution channel into the membrane tanks, and the flows goes into the membrane tanks and then out of it. The permeate pumps draw a vacuum on the inside of the membrane hollow fibers, pulling water through the membrane pores and leaving rejected solids in the membrane tank. Membrane permeate is disinfected using in-pipe UV units. One of the keys to the successful denitrification is the independent solids and nitrate recycle. What Adrian mentioned earlier, due to the membrane air scour, return activated sludge from the membrane tanks has a very high DO concentration. So introducing the stream to the anoxic zone would impair denitrification. To avoid this, the RAS is routed to the upstream end of the oxic basin. So that's this red line on the, I can't get my mouse to work. That's this red line from, so the RAS flows by gravity to the upstream end of the oxic basins, and then there are separate pumps to take the nitrified mixed liquor to the upstream of anoxic zones. There are 10 membrane trains on site. Each train has 6 cassettes with 2 blank spaces. To increase plant capacity from 10 to 13 MGD, a 7th cassette will be added to each tank. The 8th space represents safety factor to guard against any unforeseen conditions. Each cassette has 48 modules and with a surface area of 340 square foot per module. Since an MBR runs at high mixed liquor concentrations, foam accumulation is possible. The basin configuration was developed to move scum and foam to a central point where it could be wasted with the plant solids. As you can see, the the scum or foam flows from the aeration basins over the weir into the mixed liquor combined channel. And here's a gate, which can be a slide gate, and the foam and scum move into the vase and foam collection manhole. Similarly, on the membrane side, there's a backward foam removal. This configuration has worked extremely well to prevent scum and foam accumulation in both the aeration basins and membrane basins. Startup and operations. The plant was commissioned in June of 2008. The plant went from 0 to 8 MGD within 3 weeks. Plant has met all effluent requirements. The average mixed liquor suspended solids in the aeration basins is around 10,000 milligrams per liter. To keep the electrical costs down, plant has been controlling the DO within the basin to achieve a small amount of simultaneous nitrification, denitrification. Typically, the DO is tapered within each oxic basin between 1 milligram per liter at the head of the tank and 0.5 milligram per liter at the end of the tank. This has resulted in very low effluent TN numbers, and I'll show you a graph in my next slides, which shows the effluent total nitrogen from the plant. Here's a picture of the outside of the facilities. The plant wastes solids 5 days a week, 8 hours per day. No waste solid storage tank is required. The increase in mixed liquor suspended solids over the weekend is typically 1,000 milligrams per liter. The dewatering centrifuges are fed solids directly from the biological basins, and they produce a cake in the range of 18 to 20%, which is really exceptional for biological sludge. Flux management and cleaning. Membrane productivity is sustained by a variety of methods. During permeate production, intermittent air scour is applied to the bottom of each membrane cassette to prevent solids and other material from accumulating on the membrane surface. There are two modes of air scour. When the flux is greater than average flux, the 10-10 cyclic aeration is used, and when the flux is less than the average flux, the 10-30 cyclic aeration is used. In addition to air scour, for 60 seconds per hour, permeate production stops. For the first 20 seconds, the membranes are backpulsed with sodium hypochlorite solution. For the next 10 seconds, membranes are backpulsed with permeate alone. For the last 30 seconds, the membranes relax while membrane air scour continues. Maintenance cleaning occurs a few times per week. Mixed liquor is drained from the membrane tank. Sodium hypochlorite or citric acid solution is backpulsed through the membranes, and the membranes soak in the chemical solution for about an hour. Recovery cleaning is similar to maintenance cleaning, except that it occurs 6 to 12 months and is for a longer duration of 3 to 4 hours. This graph shows the effluent total nitrogen. On the y-axis is the effluent concentration, ammonia, nitrate, and TN. The blue line is the total nitrogen. Beginning August 2008, plant has been meeting the 8 milligram per liter TN goal. The fine line and DO control required for simultaneous nitrification, denitrification is shown by the occasional increase in the ammonia accompanied by very low nitrates. You can see these red ammonia blips, and the nitrates are low during that time. The total nitrogen value does not vary significantly as the sum of the nitrogen species remains the same. For a plant with TN limit only, this operation is fine, but if a plant also has ammonia limit, the operation could really be challenging, and especially in cold weather climates where you don't want to lose nitrification. This graph shows the effluent turbidity. As you can see, the turbidity has been well below 2 NTU requirement. Most of the time, the turbidity has been below 0.1 with occasional blips. Operational challenges. The plant has been in operation for more than a year now, and there definitely are some lessons learned from that. Membrane sludging. What membrane sludging really is when the membranes accumulate solids between the membrane fibers that do not allow raw water to reach the membrane surfaces. And the plant has seen membrane sludging at random locations. I will talk about it in more detail in my next slide. Membrane cleaning and permeability. The plant did not pay close enough attention to the maintenance cleans, and permeability started to decline. After 6 months of operation, the plant has been regular with maintenance cleans and have had no problems since then. Fine screening, plant staff found some material larger than 2 millimeter passing through the fine screen, for example, like dental floss. It could be related to initial manufacturing issues or problems with grouting the screen, as they saw some cracked grout. Jury is still out on this, so we'll know more. Instrumentation and control. The operators have noted that instrumentation and control associated with the MBR process requires a lot of attention. There have been numerous nighttime response calls. The city now has a full-time instrument technician at the plant. As you can see in the picture, there is membrane sludging. It occurred at random locations in the plant. Various potential causes were investigated. Air squabble mode did not appear to contribute to membrane sludging. Air tube plugging. It was found that over a time, air tubes at bottom of the cassettes filled with sludge when scour air was off and then dry out when scour air was on, but this was ruled out to this cause. The cassette installation was checked to make sure installations were plumbed and cassettes were sitting straight. Next. After investigations, it was found that the membrane fibers and cassettes shrank more than anticipated, and the cassettes had to be adjusted for slack. This slack adjustment was really labor time intensive, and the plant has recently finished this fixing the slack adjustment. This slide shows 2 graphs. Graph on the left is with recovery cleaning, and graph on the right has had no recovery cleaning. On the y-axis is the permeability, and on the x-axis is the time in months right from June of 2008 when the MBRs were in operation until August 2009. As you can see on the graph, the plant was not very regular with the maintenance clean, and the permeability started to drop. And at this point, that was after 6-7 months of operation, there was a first recovery clean which was done, and then the permeability started to get better. This on the other graph, you can see there was no recovery clean, but they have been doing regular maintenance cleaning since then. And if you compare the two graphs, there is not any significant improvement of recovery cleaning versus no recovery cleaning. So the plant has decided to increase the recovery clean interval to 1 year. The plant has 9 full-time operating staff. The plant currently operates at 8 MGD annual average flows. Overall cost to operate the plant has been $1.17 per 1,000 gallons, out of which power is the biggest one, with 49 cents per $1,000 gallons treated. That's all I have. Thank you very much.
Thank you very much, Benita. We have a number of questions for you sent in while you were talking. The first involves process selection, not specific to membrane bioreactor, but specific to disinfection. How and why did you choose UV for disinfection downstream? And did the regulatory agency allow you any benefit to using membrane instead of a conventional approach?
The UV was chosen because of there's the aquifer permit that requires on my slide. If I go back. The aquifer protection permit had the THM control, which is for best available technology. So UV disinfection was adopted for that, and it worked well with the permeate. They are like in pipe UV disinfection.
Okay. The second part to that question was, did the fact that you use a membrane bioreactor allow you to use a reduced UV dose?
For the design, I think it was the 70% transmittance was used instead of the usual 60%. So, yes.
Okay. Thank you. Next question is regarding your process selection specific to how water flows. Why did you choose a pump forward and gravity flow back, or a pump to design as opposed to a pump from design?
It's because of the hydraulics. That's what worked out to be the best.
Okay, and the third question was relative to your ammonia question. And the question is the MBR able to accomplish full nitrification? Is it specific that you're operating this plant to do simultaneous nitrification denite? Is that why your ammonia jumps up and down?
So the plant was not designed to do simultaneous nitrification, denitrification. It was for complete nitrification, but the operators are trying to operate it this way to save some on the electrical costs. So yes, MBRs can achieve a complete nitrification. That shouldn't be a problem.
Okay, and last question for you. You had mentioned on the weekends the solids level went up. Do you know how high the solids level went in the membrane tanks?
Yeah, it went up by 1,000 milligrams per liter.
To 10, 11, 12,000, or do you know the total?
Yeah, it was, usually it is around 10,000 milligrams per liter, and it went up to 11,000 milligrams per liter.
Okay. All right, thank you very much. We'll have some more questions for you at the end of the third presentation.
Thank you.
Let's switch over to our last speaker. Our last speaker is Mary Carr Portillo, a supervising engineer with MWH in Las Vegas, Nevada. She's going to speak about a tertiary case study in Clark County, Nevada. Mary?
Thanks, Paul. Can you hear me?
Loud and clear.
All right, great. Okay, so I am going to talk this afternoon or this morning over on the West Coast where we are about Clark County Water Reclamation District here in Las Vegas and their case study of how and why they went to tertiary membranes. Let's see. Renee, I'm not having full movement of my slide.
Mary, did you try the opaque arrows in the left-hand corner?
Yeah, I'd try that one, see how many it'll go over. Working? Not working.
Click one more time for me.
Oh.
There you go.
Gonna now go two clicks. All right, well, I'll hit this slide while it's there. We're going to go through the introduction of the project and then talk about the design criteria of the membrane system, and then discuss why the district, Clark County, went to tertiary membranes rather than MBR. Discuss a little bit about the pilot testing that's being conducted right now, and then talk about the design characteristics that we evaluated through design, and then wrap up with some of the operational challenges that we've found through the design and the pilot testing to date. The project objective, as many projects for wastewater and water treatment plant expansions are pretty much based on water quality and water quantity. Right now, the district's membrane facility, their immediate filter facilities, some of them are upwards of 30 years old, so they need to replace some capacity that they have out there. In addition, they have taken a proactive approach to protecting the region's drinking water supply, and next slide here kind of shows you why. We have a unique situation in Las Vegas where we discharge and pull out of the same body of water for our wastewater and our drinking water. This is Lake Mead, and over to the right is the entrance to Lake Mead through the Colorado River. And then water flows generally down to the Hoover Dam, and along the way we have one inlet from the Las Vegas Wash, which is where all of our wastewater dischargers discharge to. It flows into the lake, and then we have our drinking water intake, which is out here in the lake a bit, basically between the discharge and the Hoover Dam. So you can see that having the wastewater community in Las Vegas is really interested in water quality going into the lake, as is our drinking water entity. The next picture I show is one of the reasons why water quality has become such an issue in Las Vegas. You can see there's a white line basically around the lake here, and lake levels have been dropping over the last 7 years or so, And as that lake level drops, the mixing and dilution of wastewater into the Lake Mead or Colorado River water is reducing, and also it is pushing out the potential for algae blooms to move closer and closer to our intake. So big issues with just some of the environmental effects in Las Vegas. Well, Renee?
Mary, are you in your PowerPoint window? You're good?
Okay, I'm not seeing my, here we go. There we go. Sorry about that. So the next slide we have here is the process flow diagram, and basically what we're going to talk about today is this area. We are doing tertiary membrane filtration. We have direct filtration in that we inject alum pre-screen to the pre-screens, and then
Mary, sorry, we're still on Hoover Dam.
Are you? Not on my screen. Hang tight. Do you see my full presentation?
Yep, good.
So if I go to slideshow, it should pop up?
Let's try that.
How's that?
Perfect.
Okay. Be honest, Renee. Okay, so the process flow diagram, like I was saying, we're using direct filtration. We'll have alum injection followed by screening, and then we're using submerged membranes, similar to the MBR membranes that were discussed in the MBR case study, but kind of a different operation. We follow our membranes with ozone system disinfection, and then on out to the Las Vegas wash. One of the, as we talked about the drivers for treatment, one of the main drivers for treatment is phosphorus removal. I know we talked a little bit about nitrogen removal in the last case study, but phosphorus removal, or phosphorus is the nutrient of concern in Lake Mead. So reducing that as much as possible is the goal. So looking at the design criteria and the design parameters that we looked at, we're designing a 30 MGD membrane facility. We have piping and pumping up size to accommodate 42 MGD. And basically what this is for is so we can expand without having to parallel or dig up a bunch of piping and pumping work. We can utilize some increased capacity in the membrane if possible. We have a drum screen that's 500 microns. That's in contrast to the MBR case study we just heard was 2 millimeter screens. So we're significantly smaller. And then the membrane flux that we're targeting is 20 GFD, which is about the same as what that MBR case study was at. And then as Adrian talked about the membrane recovery, MBRs don't typically have membrane recovery as a design criteria or driver, but in tertiary membranes are more towards a drinking water application. We run at a 92% target recovery. So that means for every 100 gallons that go in, we should be able to have 92 gallons of treated effluent that can go out to the wash. So looking at our wastewater characterization, talking about the phosphorus, the secondary effluent, so after the secondary process and clarifiers, we have an average of 0.4 milligrams per liter of phosphorus, and then that can blip up to 6.2 milligrams per liter on a bad day coming in. In contrast to the MBRs, we're looking at the TSS level of about 13 with a maximum of 50. So so much less. It's more of a murky water that is pretty clear. You might see a few little things growing in it, but for the most part, you don't see the particles, individual particles that are in the water. And then again, our target effluent quality is looking at turbidity of 0.1 NTU average and a 0.15 NTU max. Now that is much closer to what a drinking water facility would target than what an MBR would target. I believe that Benita's targets were less than 2 NTU, and they were happy with a max of 5. So you can see there's a significant reduction in expectations of how the effluent turbidity should be on the tertiary membranes. So why did the district pick tertiary membranes? And the real driver is phosphorus reduction. They are comfortable with their secondary process. They like their clarifiers. They have spent a lot of time over the last probably 10 years, maybe more, optimizing phosphorus reduction in their secondaries. So they already get down pretty low. 0.4 is significantly lower than other areas in the country, but not quite low enough for the valley here. So that's why they went towards tertiary. Why not MBR? And again, they like their optimized MBR, secondary process. Retrofitting wasn't a strong driver for them. They have plenty of space, so that wasn't a real issue for them. So let's talk a little bit about the pilot testing, kind of wrap up the design criteria and the setup of the design, and we can go through the pilot testing and how that's going right now. Here are a couple photos of the pilot, and in the back here we show the coagulation tank, and we've got chem feed. Here's the pump and works, but it's piped to the other side of the tank and dosed into a line feeding into this tank. We've got a couple different types of mixers that we're testing out, and thankfully this tank is about the same size for detention time as our direct filtration through our screening will be to our full-scale membranes. Have about 10-minute detention time. Also, we have a show on the front of the membrane skid is the HMI and PLC. Adrian talked about the automation and the potential for automation. This does take a little bit of hand-holding, probably more than MBRs, but by and large, it's a more technical and highly automated process in general. The pilot itself has some manual parts to it that would typically be automated in the full scale. And then down here we show the blower that will that generates the air for our air scour during our back pulses. Looking at the other side of the skid, we've got a filtrate pump and a back pulse pump that we use to pull and push water through the membranes for normal operation or forward flow operation, and then back pulse cleaning operation. This actual photo was taken before operations were some SCADA modifications were changed in the control, and you can see there's a significant amount of foam that kind of lived on top of this tank for about 3 months. The reason for that was the blower was running full time, and the membrane stayed clean, but the power consumption was incredible associated with that, and not needed for the tertiary full time for tertiary filtration. So once we turn the back pulse, turn the blower to only operate during the back pulse, the foaming and the bubbling went away. And then also of note on this skid, we have an air system for the membrane integrity testing, which, like I've said a few times before, this operation is moving more toward the drinking water type operation than typical wastewater applications. So the district asked for this capability on not only their pilot but on their full-scale system so that they can see why, if they get a high phosphorus levels or high coliform levels, they can go check and see why and where that might be coming from. So we've run a number of runs through the membrane over the last few months, and run one, each run we're varying the alum dose. So run one we ran at 4 milligrams per liter. Run two we ran at 6 milligrams per liter, and then run three we're kind of working out what might be a high end, and started at 10 milligrams per liter and failed miserably over the first 2 or 3 days. So backed off to 8 milligrams per liter and did a little bit better, but not too much. And then we've just started where we had this data set was collected right as we had started the 6 milligrams per liter again. The target, we've talked about cleaning cycles. The start and stop of each one of these runs is basically a recovery clean. Our target for tertiary membrane filtration recovery clean interval is 4 to 6 weeks. That's a significant contrast to MBR that, what we just heard, they're running at once a year and fine with that, happily running at that. And so typically 6 months to a year you might recovery clean your membranes. But in the tertiary filtration, we're using significantly less air to scour, and in tray we've got to chemically clean more often. So you can see that the 3-week run at 4 milligrams per liter didn't quite make what we had expected to get to our 4 to 6 weeks. However, we didn't do a maintenance clean the first week. We are operating in a weekly maintenance clean, followed every 6 weeks with a recovery clean. And we didn't do it the first week because we were going so well. We thought we'd try and push it. Well, we pushed it and fouled out the membrane faster than we had hoped. So after we finish up this 6 milligram per liter run 3, we'll go back down to a 4 and reevaluate the ability to go to 6 weeks with a lower dose. The associated phosphorus removal with each one of these runs, phosphorus is pretty directly correlated to how much alum we're using. The alum is used to coagulate just enough of the phosphorus just big enough to be captured by the membrane. We don't need these big fluffy flock, but we need something that's big enough for the pore to capture, or the membrane to capture. So what we've noticed in the data is that increased levels of alums, you do see an increased reduction in phosphorus. The downside is if we get too high in alum, we bind up our membranes pretty quickly. So once the pilot has been running for, I don't know, 6 months now or so, and we've gone through a lot of operational changes through, just HMI changes and control changes throughout it. In the meantime, over the last 3 years, we've been developing and designing the full-scale facility. So I'm going to take a few slides and talk about what the full-scale design entailed. We have our facility. This entire area of the Clark County's plant is dedicated to tertiary treatment, and what we have are existing media filters that are about 30 years old. in parallel to where we're going to be putting our membranes and ozone equipment. Above the media filters, we have some flux basins that are actually out of service. They don't use them now. They don't use a lot of this equipment up at the top here either. That once was a lime clarification tertiary filtration facility that like I said, they've optimized their secondary treatment so much that they've gotten away from a lot of this chemically intense process. So the kind of the purpose of this slide is to show that the footprint of what we're looking at adding, membranes and ozone, is small in comparison to the massive footprint that was designed 30 years ago. A little bit more detail of where our equipment is going to go. Again, here's the media filtration, existing media filters to kind of get you lined up. We will be retrofitting the drum screen into these flock basins up here, and then have room for expansion of our membrane building for an additional 30 MGD. We also have a tunnel that will eventually meet up with a enclosed building that will eventually hold ozone and membrane equipment. For this phase, though, we designed equipment pads with shade structures. And then we have an ozone contactor, and important to kind of isolate your acid waste away from the rest of your waste. So we've isolated the acid waste so it can go to the head of the plant. In comparison or contrast to Benita's photographs, we have a architectural rendering of what our facilities are going to look like. A little bit less flare than the Arizona facility, but we're out in the desert. This is pretty far out there in the desert, and it's functional and operational. We have an enclosed building for the membranes themselves. And then again, 2 shade structures holding the ancillary equipment for the membranes and the ozone equipment. So we've got, this hasn't been built yet, so I don't have any photos of what the real deal looks like, but we've got some 3D cuts of the design. This is the membrane building. The design is 2 trains with 6 cells for each train. 1 train is aligning right here with 6 cells, 1, 2, 3, 4, 5, 6. There's a parallel train on the back side of this building that runs on the other side. Each one of these cells has a dedicated filtrate pump that's located in a lower level, so it's submerged, and then suction. Excuse me, it's a flooded suction. And then we've got piping and piers down at the bottom level. Our soils aren't the greatest, so we've had to bulk up the structure a little bit. Again, we have this tunnel over here that will eventually go into the ozone building and hold the membrane ancillary equipment. But functionally today, or functionally as designed, it also is the chemical injection point and heating area where we heat up any of our cleaning solutions so that it'll more effectively clean. And here's the membrane equipment pad. We've gone through some of the ancillary equipment in the other slides, but we have 2 blowers. And then behind here we've got 2 compressors, which the compressors are used for the air actuated valves, as well as the membrane integrity testing air. Then we have in the back here, we have recirculation pumps for our cleaning solutions, and then over here we have space allocated for the potential of having a softened water system for cleaning. The water out here in the valley is pretty hard, and the thought was mixing bleach with hardness might have some precipitation to it. So we've allocated some space for a softening system if that's needed. And in the back side here, we've got filtrate tanks so that we can have some water ready and available for the cleaning solutions as it's made. So when we walk through the design, we're at a facility that's existing. It's old. old. A lot of the equipment doesn't work anymore, or they don't use the equipment anymore. So we went through each structure and said, can we use this structure for what we're doing in this expansion? Does it fit our needs? And basically there was a yes, there was a maybe, and there was a no. The drum screens we did select as to retrofit, and I'll show a retrofit 3D of that in a second. And then the membranes, there is the possibility for retrofitting the existing media filters with membranes in the future. The downside of it is retrofits typically are more expensive, more complicated construction-wise, and it has to be worth what you're saving in concrete to actually go towards retrofitting membranes. But still definitely on the table as far as a possibility in the future. And then we looked at the ozone contact basin, excuse me, the existing chlorine contact basin, and since we're going to ozone, looked at it to see if it would be appropriate for an ozone contactor, and basically came down to no, it's the wrong size, kind of wrong length to width ratios for ozone contacting. So here's some photos. I'm going to walk through how we retrofit, or how we're going to retrofit the drum screens into the existing concrete structures. And here's a few photos of what these drum screens look like. This is in contrast to the band screens that are being used in Benita's case study. Band screens can't go down to a 500 micron screen size, and there are other screens out there that can go down to 500 micron, but not at the flow rates that we're looking at. We're looking at a 50 million gallon a day screen here. So kind of only a couple selections of what technology is out there that is appropriate, but here's one, and the flow is from the inside of the drum to the outside, and basically flow comes in, around, and then out the screen, and we'll take you to a cut of it. Flow comes in, is split around the drum screen, and then into the Ferris wheel type drum, and then moves through the screen, and filtered water, screened water, moves out towards our membranes. So all of the concrete, the colorful concrete is new concrete, but you can see a significant amount of it is able to be retrofitted or reused. So looking at also going in parallel, or having a parallel installation to an existing facility, we had a significant number of hydraulic interfaces that we had to keep in mind when we were designing. A quick look at the hydraulic profile. We're kind of all over the place, but this is determined basically from the existing facility, and then we're able to use pumping where necessary to achieve those hydraulic, the existing hydraulic profile. We're tied at the front end from the FIPS with their filter influent pump station. They have existing capacity in that pump station. And we're tied at the back end at their outfall, basically, hydraulically. So we utilize a pump in the middle to get our flow through. And then this is just a flyover view of all of the tie-in points that we have. Here's our tie-in to FIPS, the filter influent pump station. We then tie into the existing structure for the drum screen. I have the media filters are in purple because they're not necessarily directly tied today, but have the potential in the future to be hydraulically tied to our membranes if they're retrofitted. And then we have our wash water system that we're going to reuse, and then tie to the outfall or the ERW system, which is their plant water. So looking at to wrap up the design portion, we looked or have evaluated through design and the pilot testing some of the operational challenges that the district will have to deal with along the way, or design has dealt with along the way. Thinking back to the 3D of the membrane basin, you can see that there's 12 cells that are operating at any given time, and we have backwashing sequencing going on, or backwashing going on every 20 minutes or so. So if the sequencing isn't controlled, then we could theoretically have all of these systems, all of the cells go into the backwash at the same time, or go into a tank drain at the same time and overload a system, and then at the same time not being able to take the water that's coming to it. So having the backwash sequencing correct is critical to the process. Another thing that we've come through with the pilot testing is that membrane integrity testing for wastewater treatment plant operators is a whole new ball game for them. There's not a whole lot of research or experience out there with doing membrane integrity monitoring with air pressure decay tests. And so getting the results from a membrane integrity test, how does that, should we evaluate that in the same way that we evaluate drinking water facilities? So we're working through those questions. And then once we do find fibers that are in need of repair, the water quality is still good, or we check the water quality, see if it is still good. If it's not, is it time to repair, or do they let it go a little bit longer? The mechanics of, or the design of repairing a fiber is a syringe and glue, and you're handing this to an operator that's used to handling a wrench and big equipment, and you pair that up with wastewater and a syringe, and the potential there could be a little uneasy with using the equipment or using the tools. So we're working through some other options for fiber repair and getting their comfort level up to par, and then the operations staff able to be ready for the plant when it comes online. So to recap, we talked a little bit about water quality, and phosphorus is the key here. We went through the design and the pilot testing and some of the results, and then reviewed the operational challenges and how the operations staff is going to be able to take over this new facility when it comes online. And with that, if there's any questions, I'll be happy to take them.
I have a number of questions for you.
Sure.
First one is specific to your project. What are the engineering, capital, and O&M costs for the plant? Do you have those at this point?
We actually have bid numbers that were yesterday reject all bids. So it's around $55 million, in that ballpark. Somewhere we've had several bids that have come in between 50 and 60 million. That's including the ozone system.
And that's current construction pricing?
Yes.
What about the other ancillary costs, the engineering costs, and have you done an estimate for O&M?
We have not completed an estimate for O&M since the preliminary evaluation or preliminary design phase, and I don't have those numbers off the top of my head. I know that we're slated to round up those numbers over the next few months. Okay,
next question is regarding the Clark County plant. How do they do phosphorus removal? This is an obvious tertiary plant, but how do they do the phosphorus removal upstream of that?
Sure, they have a activated sludge conventional secondary process with that was shown in several of the slides, the introductory slides.
Okay, what's the regulatory discharge limit for phosphorus, and what are you seeing out of the pilot test?
Regulatory limit. We are significantly lower than the regulatory limit. I don't have the regulatory limit off the top of my head. we are discharged, or our pilot testing is seeing an effluent of 0.05 and lower. So about 1/10 of what's going in from the secondary process. And that is significantly lower than the regulatory limit. The point being that the district is really trying to push these as low as they can go, way beyond what the regulations are right now.
Okay, next question is an easy one. Regulatory limits on reuse water from membranes are 0.2. Did you see that being a problem with the tertiary filter?
0.2 NTU?
Okay. 0.2 NTU, sorry.
No, not at all. You know, I mean, as with instrumentation goes, you always get these blips, and half the time, or I'd say 90% of the time, it's some issue with the instrument. So you always get blips, but actual water quality, no, not at all.
One of the challenges, I mean, if you have a water plant basically downstream of a wastewater plant, one of the challenges there is going to be the hydraulics relative to the fluctuations in the influent wastewater. How are you handling the fluctuations in diurnal, I guess a diurnal curve in that tertiary water plant?
This actual facility is a base load facility. They have a plant, their whole, the rest of their process, their pre-process is across the wash at a different facility, and basically they use this filter influent pump station to base load over to the media filters today and later on in the future to the membrane filters. So at this time, we don't have too much to concern about diurnal fluctuations. The design has been included to go up to 42 MGD of peaking, I guess is to say, and if they choose to run that way, they can. If not, they've got several other options they've got other media filters on the other side of the wash that are not as old and fully functioning, and they've got other options to deal with their diurnal curves.
Okay. Thanks very much. Keep the questions coming, folks. We have some more time here. I am going to address the next few questions back to Adrian, but keep the questions coming for Benita and Mary. The first one for Adrian is regarding metals removal in an MBR. Is there a number or a relative efficiency of metals removal in an MBR compared to a conventional plant?
Well, an MBR it does run at a pretty high SRT, solids retention time, and what that generates is a hydrophobic sludge, which tends to absorb metals generally than treatment plants that would operate at a lower solids retention time. So a general comparison of an MBR at a long SRT compared to a conventional plant at a shorter SRT, you would expect the MBR to remove more metals because you get more absorption on the sludge.
Okay. Next question for you. On this webcast, there's people that are looking at conventional compared to membranes, and we're introducing them to a new concept of membranes. What are the advantages of tertiary membrane filtration over granular media filtration?
Well, the first one is a higher effluent quality. So if we go back to one of my introductory slides, we looked at a filtration spectrum compared to filtration technologies. So media filters have a larger pore size and therefore have a lower removal. The other thing that happens with media filters is that you can get some breakthrough in a media filter, which the membrane is pretty absolute barrier. So you would expect that you'll get better removal generally with a membrane as opposed to a media filter.
Okay, and my third question for you, again, these are people that are just starting to look at membranes. Mm-hmm. What do you and the industry in general say about the design life of membranes in wastewater? What is the life of a membrane that is taken care of?
Well, as a young professional, I am going to throw a number that has been given to me by others, which is 10 years. And to be honest, Paul actually gave me the answer to that question earlier. And so 10 years is, I guess, the rule of thumb that other more seasoned professionals have provided to me, and so that would be the number that I would pass on as an expected life.
I might interject, actually. This is Mary.
Okay.
Depending on what type of membrane you're using versus the MBR membranes tend to be a stronger, more robust, just physical fiber. So they probably will have a longer life to them than maybe the unsupported membranes that are a little weaker and typically used in a drinking water application. I typically, when I'm asked this question, I typically give a range of years, and manufacturers always want to tell you 10 years or 15 years or infinite time. And engineers want to be a little bit more conservative and say, well, there aren't any out there that have been running for 10 years, or maybe there's only a handful that have been running for 10 years, and there's others that haven't made it yet. And so I typically give an answer between 5 and 10 years, and design for 7.
Okay, good. Thanks, Mary. I wonder, maybe since we're on the call, I understand that tertiary membranes in wastewater applications would be actually more robust than the membrane that you would put in a drinking water plant because it's a more severe environment. Is that, would you agree with that assessment?
We did use the same membrane that the MBRs use for the Clark County. What's that?
For your tertiary filters.
Yeah, it's the same exact module, basically. That isn't to say that you can't look at other stuff. As part of our evaluation, we did look at other types of membranes and unsupported membranes, and basically the client drove the decision of wanting to use the most robust thing out there. But manufacturers certainly are willing to sell you something that they have to sell. And there's experience out there in wastewater with unsupported membranes, I believe.
I have something more to add. The life of membranes, most vendors have started to tie the membrane warranties with the upstream screenings. If you have like a 1 mm screen, fine screen versus a 3 mm fine screen, so that also plays into the whole how long your membranes are going to last, is how what they have upstream of them, the barriers they have.
Yeah, as a membrane manufacturer, I would say things will last as long as people take care of them. And taking care of membranes means everything from protecting them, screening, clarification, cleaning, treating them gently, and paying attention to them. So it is kind of a relative question, but it's also relative to how well you take care of them. I'm going to shift to Benita now, and we've got some questions specific to the Butler Road plant. Do you have an estimate of the engineering and capital costs for that Butler Road facility?
Actually, I can't remember it right away, but I can get to that, like email, or that shouldn't be hard to find. I don't remember it.
Okay. Next question is regarding cleaning, and do you recall the chemical concentration that they use and what they do with the solution after they clean the membranes?
For maintenance clean, they use relatively lower dose of 100 milligrams per liter of sodium hypochlorite. For recovery clean, they did recovery clean only one time. They cleaned 6 out of their 10 tanks, and they did not go all the way cleaning all the 10 tanks. They used the sodium hypochlorite solution of 10,000 milligrams per liter and citric acid of 1,000 milligrams per liter. And the maintenance cleans are done 2 to 3 times a week.
Okay, thank you. And one last question for Mary. And you may have said this. What do you do to dispose of the concentrate for Clark County, and where does the filtrate get discharged to?
We have 2 avenues for our waste. Any of the hypo and just clean non-chemical waste goes back to the clarifiers that they have on the property there that is adjacent to the facility, adjacent to the membrane. The acid waste will go to the head of the plant and go so that it can go through a biological process. The issue with acid waste is that it can really mess with your coagulation, and even if you neutralize it, it can still have the chelating effect of and not let you coagulate, which is the point of having the alum addition for phosphorus removal. So we separate it and let it go through the biological process again, which seems to break down that constituent that doesn't let it work with the alum. Yeah, that was your question. Okay. Yep.
Okay. Well, that about summarizes all the questions. I did get a number of comments on the excellence of the quality of the speakers and the quality of the presentations. Remember that this was done by the WEF Young Professionals Committee, and I'd like to thank all of you speakers for contributing today, and thank you for attending our webcast.
Thanks, guys. Appreciate it.